Have you ever looked at someone and wonder, what is going on inside their head? Well, I'm here to answer not that question. I'm here to answer the questions about multiple bonds. Greetings everyone, my name is 𝐁𝐎𝐍𝐃𝐒 alongside my partner 𝐼𝐗𝐿𝐴, whom you will be meeting in the later minutes of this discussion video. This is in accordance to the performance task given to us by our Advanced Chemistry Advisor, Sir Roland Labad. And without further ado, let us begin. Let us commence discussion.
Now, let's proceed to our lesson's objectives, which are: first, describe multiple covalent bonding in terms of atomic orbital overlap. Second, relate the concept of resonance to pi bonding and electron delocalization. Now, the subtopics we'll cover for today are: first, hybridization; second, sigma and pi bonds; and third, multiple covalent bonds. These subtopics will help you understand today's lesson thoroughly. Now, let's proceed to our first topic, which is about hybridization. When it comes to multiple bonds like double or triple bonds, hybridization plays a key role in explaining molecular shapes and bonding characteristics. Hybridization is a way to describe how atomic orbitals mix to form new orbitals for bonding in molecules. When atoms form multiple bonds like double or triple bonds, hybridization helps explain the shapes and bonding. For example, sp3 hybridization, which involves one s orbital and 3p orbitals combined to form 4 sp3 hybrid orbitals. Like for example, methane, which has a chemical formula of CH4. Second, sp2 hybridization, which involves one s orbital and 2 p orbitals combined to form 3 sp2 hybrid orbitals, like the ones found in boron trifluoride or BF3. Third, sp hybridization, which also involves one s orbital and one p orbital combined to form 2 sp hybrid orbitals, for example, in acetylene C2H2. Now you might be wondering, how does each of the hybridization always has one s orbital? We'll learn it again as the slide progresses. And have you ever wondered what the purpose of hybridization and what is its importance? The purpose of hybridization is to explain the true three-dimensional shapes of molecules, which simple atomic orbitals cannot do on their own. And hybridization and its importance is that hybridization helps to explain the observed shapes of molecules by allowing for the formation of equivalent molecular orbitals. Now, how can we easily identify an atom's hybridization? We can exactly determine an atom's hybridization by using the formula of Z is equals to 1/2 times number of valence electrons in central atom plus negative charge minus positive charge plus number of monovalent atoms, which involves hydrogen, fluorine, chlorine, and bromine. Let's plunge headfirst into the thrilling quest of nailing down an atom's hybridization. First up, the mighty steric number. This counts up the electron density regions around our central atom. It is also defined as the total number of regions of electron density or electron pairs around the central atom. We also have another formula to calculate for the steric number, or Z, which is number of bonded atoms plus number of lone pairs of in the central atom. But for a more precise answer, use the formula provided. Next, we have the valence electrons, which are the negatively charged particles or electrons found on an atom's outermost shell. A handy tip: you can spot the valence electrons of an atom by simply analyzing the group that element belongs in to fast-track your hybridization detective work. What this means, again, is you simply have to look at the group the element belongs to determine its number of valence electrons, and in fact, the number of valence electrons corresponds to the group number, the group of electrons it belongs. Then, we have the monovalent ions, which are atoms or clusters with a single positive or negative charge. If the monovalent atoms are not involved, we'll take 0 as to be put in as a value in our formula. Now, why exactly are hydrogen, fluorine, chlorine, and bromine considered monovalent atoms? These elements are considered monovalent atoms as they have a valency of 1 and can only form 1 bonds, as, as they tend to gain 1 electron to achieve a stable electron configuration, hence satisfying the octet rule. Octet rule? What does this mean?
The octet rule is a chemical principle stating that atoms tend to bond in a way that gives them 8 electrons in their outermost shell, achieving a stable electron configuration similar to that of a noble gas.
Next, to determine an atom's hybridization, we use the hybridization formula to find the value of Z, which represents the steric number or total number of electron regions around the central atom. Once we have calculated for the value of Z, we simply match it to this table to identify the hybridization type and geometry. For example, if the value of Z is equals to 2, the hybridization is SP, with it having a geometry of linear. If Z is equals to 3, we have the hybridization of sp2 with trigonal planar as its geometry, and up so on until the value of Z, which corresponds to its different hybridization and its different geometry, which includes sp3, sp3d, sp3d2, and sp3d3 in the hybridization, and tetrahedral, trigonal bipyramidal, octahedral, and pentagonal bipyramidal as their geometry. Let's apply this to a few examples. First, for carbon dioxide, carbon has 4 valence electrons, no charge, 2 bonded atoms, and this will equate to. Second, for NH4+, nitrogen has 5 valence electrons. Subtract 1 for the positive charge, plus 4 hydrogens, which will equate to. Next, for NO2-, nitrogen has 5 electrons. Add 1 for the negative charge, and no monovalent atoms are involved in this example, and it will equate to. For SO4 2- as its charge, sulfur has 6 valence electrons. Add 2 for the charge, and no monovalent atoms are involved, and it will equate to. To simplify, this method is quick, systematic, and works for a wide variety of molecules and ions. Once you determine the value of Z, determining hybridization becomes as easy as matching it to the table of values as shown in the slide. Now, let's proceed to our second topic, which is about sigma and pi bonds. Now, what are sigma and pi bonds? What do you think it is?
Is it perhaps the ones that connects two atoms with each other?
Yes, that's right. In fact, sigma and pi bonds are 2 types of covalent bonds that differ in how atomic orbitals overlap and interstrand. A sigma bond is formed by the head-on overlapping of orbitals along the internuclear axis. This results in strong overlap, making the sigma bonds the strongest type of covalent bond. Every single bond is almost always a sigma bond, and in multiple bonds, there's always one sigma bond. The electron density is symmetrical around the axis, allowing for rotation of bonded atoms. Additionally, sigma bonds are found in compounds such as alkanes. On the other hand, pi bonds forms through sideways overlap of unhybridized p orbitals above and below the internuclear axis. The overlap is weaker, so pi bonds are less strong than sigma bonds. Pi bonds occur only in double and triple bonds alongside a sigma bond, and they restrict rotation because breaking a pi bond requires extra energy. And to differentiate sigma bond and pi bond, simply pi bond and sigma bond can also differ in how they need to release or they need extra energy for these bonds to rotate as what was stated. And additionally, pi bonds are also common in alkenes and alkynes where they contribute to the molecule's rigidity and reactivity. As shown in the figure shown in the slide, it shows that sigma bonds is the head-on overlapping between two atoms. Meanwhile, the pi bonds is the side-on overlap between two different atoms. And again, pi bonds requires extra energy for it to be rotated. Meanwhile, in a sigma bond, it doesn't require extra energy for it to be rotated as it doesn't require extra energy again. In short, sigma bonds form the basic framework of molecules, while pi bonds provide additional bonding that affects the strength, shape, and reactivity of compounds. Now, let's proceed to our third topic, which is about multiple covalent bonds. First, what are multiple covalent bonds? Based on its definition, multiple covalent bonds are a chemical bond where two atoms share more than one pair of electrons, resulting in either a double bond where two pairs are being shared or a triple bond where three pairs are being shared. Additionally, a multiple covalent bond is formed when two atoms share more than one pair of electrons to achieve a stable electron configuration, typically satisfying the octet rule for stability. As provided in the figure, it shows that double bonds, triple bonds truly does differ to each other. But how do they really differ from each other? Well, double bond is a covalent bond where two atoms share two pairs of electrons, which will total to 4 electrons that's being shared between two atoms. It is represented by two parallel lines in structural formulas consisting of one sigma bond and one pi bond. As shown in the picture in the slide, it shows that there are two central atoms or there are two carbon atoms or hydrocarbons that are sharing electrons in order for both the carbon to achieve stability aside from the hydrogen. So to count, a double bond again requires 4 electrons total to achieve a stable electron configuration. So in here, we can count whether if both carbon now satisfies the octet rule by achieving 8 valence electrons. So to count the valence electrons or the total valence electrons now that both carbon atoms are being shared or sharing electrons, we can count the valence electrons or the electrons in carbon by using the yellow circles. First, 1, 2, 3, 4, 5, 6, including the blue circle which are the electrons that's being shared by the carbon on the right side. 7, 8. And there you have it. We now have 8 total valence electrons by sharing through a triple bond, which is also shown or provided as the figure below the electron atoms. The key characteristics of a double bond consist of: first, in the composition, a double bond consists of one sigma bond and one pi bond. In terms of strength and length, double bonds are stronger and shorter than a single bond, but weaker and longer than a triple bond. In terms of reactivity, double bonds are generally more reactive than single bonds because of the extra electrons being involved. A few examples of a double bond consist of: first, CO2 or carbon dioxide, wherein the carbon atom is double bonded to each oxygen atom. Second, O2, which involves two atoms that share electrons within each other, wherein each oxygen atom shares a pair of electrons with each other to achieve a stable octet. Third, alkenes, which are organic compounds that contain a carbon-to-carbon double bond like ethene, which has a chemical formula of C2H4. Next, triple bond. A triple bond is a chemical bond where two atoms share three pairs of electrons for a total of 6 bonding electrons, or 6 electrons that's being shared to achieve a stable octet. It is also represented by 3 parallel lines consisting on 1 sigma bond and 2 pi bonds. So to differentiate triple bond with double bond in terms of representation and the composition, double bonds includes 1 sigma bond and 1 pi bond, wherein in triple bonds, it consists of 1 sigma bond and 2 pi bonds. And in terms of representation, in double bonds, it is represented by 2 parallel lines, and in triple bond, it is represented by 3 parallel lines. As shown in the picture provided in the slide, it shows the sharing of 3 pairs of valence electrons, wherein atom A and atom B are sharing a total of 6 bonding electrons, which is an indicator of a triple bond. And in order for us to really identify if both atoms now achieves octet rule, we can simply count again using the electrons that's being shared or is being labeled in red or in blue. Its key characteristics composes of: first, bond composition. A triple bond is made of 1 sigma bond formed from the direct overlap of atomic orbitals and 2 pi bonds formed from the side-by-side overlap of p orbitals. Its strength is: triple bonds are generally stronger and shorter than single or double bonds between the same two atoms. A few examples of a triple bond are: first, nitrogen ion, which has a chemical formula of N2. It shows that between two nitrogen atoms, there are a total of 6 valence electrons or electrons that's being shared to achieve a stable octet. And for us to identify or for us to clarify whether it truly achieve the total of 6 or 8 valence electrons, we simply have to count 1, 2, 3, 4, 5, including the electrons being shared, 6, 7, 8. There you have it. We have 8 valence electrons that's being shared. Second, cyanide or Cn-. It shows that between carbon and nitrogen in cyanide, it shows that there are a total of 6 valence electrons that's being shared to achieve a stable electron configuration. Third, ethene, which has a chemical formula of C2H2. Here, it is a hydrocarbon which involves not only one but 2 different elements. Here, it's shown that C or carbon as the central atom is sharing a total of 6 valence electrons in order for both carbon atoms to achieve stability. And in case you're wondering why and how does it have a total of 8 valence electrons now that there's only 7 red dots? And to clarify, in order for an atom to achieve, or in order for a molecule to achieve stability, again, it has to have 8 valence electrons. So we have to count the blue dot that's being shared between the bond between carbon and hydrogen. And hence, Now we achieve a stable octet rule, or now we achieve the octet rule.
Now here is ethene. In ethene, each carbon atom is sp2 hybridized and the sp2 orbitals and the p orbital are singly occupied. You can see that here. The hybrid orbitals overlap to form sigma bonds, while the p orbitals on each carbon atom overlap to form a pi bond. This is the given hybridized sp2, as you can see in the definition. Well, to the left, this is a singly occupied p orbitals. Together they overlap to create a pi bond. Now, moving on, in the acetylene molecule, which is basically still ethene, C2H2, which is its compound, the elements that make up for it, there are two CH sigma bonds and a C triple bond involving one C sigma bond and two C pi bonds. Now, where can you look for these? Now, if you look at this illustration above, this is where you'll see everything, right? So, you see these overlapping things? These are simply or easily the sigma bonds, as we know. And the ends that do not meet, those are pi bonds. These could also be pi bonds right here. Now, the difference is sigma bonds are a bit stronger. No, not a bit. They are indeed stronger, while pi bonds tend to be weaker. The dashed lines, each connecting two lobes, indicate the side-by-side overlap of the four unhybridized p orbitals. Basically, what I pointed out earlier. This shows the overall outline of the bonds in C2H2 or acetylene. The two lobes of each of the pi bonds are positioned across from each other around the line of the CC sigma bond. As you can see, these, the ones that I pointed out earlier. Now, let us do a quick recap of hybridization. Hybridization involves only sigma bonds, lone pairs of electrons, and single unpaired electrons or radicals. Structures that account for these features describe the correct hybridization of the atoms. However, many structures also include resonance forms. Remember that resonance forms occur when various arrangements of pi bonds are possible. Since the arrangement of pi bonds involves only the unhybridized orbitals, resonance does not influence the assignment of hybridization. Here is an illustration of the molecule benzene that has two resonance forms. You read the text. Each carbon is bonded to three atoms with no lone pairs, indicating sp2 hybridization. The unhybridized p orbitals form pi bonds which are delocalized rather than fixed in one position. Since valence bond theory can't fully explain this, molecular orbital theory gives a better description. Now I will be discussing this further. Now benzene is a six-membered carbon ring. As you can see, there is six molecules of carbon and also hydrogen. Now each of these elements is structured drawn with an alternating single and double bond. As you can see, single, double, single, double, single, and another double. The two structures, as you can see, are identical. They only differ in the placement of the pi. One has the double bonds in one set of positions and the second structure has them in the other set. As you can see, it is basically like a mirror. They are connected by a double-headed arrow to indicate that they are resonance forms, as you can see. Now for clarification, neither of these structures represent the actual molecule. Resonance structures are imaginary representations only. The molecule does not switch back and forth between these two. These are merely tools to help us visualize the structure, which is a resonance hybrid.
There comes our lesson. Thank you for listening. Thank you.